doing this Polyaxial testing on some particular rock specimens. From that day till still I always say to my students also that I consider K.S. Rao sir as the father of rock mechanics. And sir, it's really a great privilege that sir you accepted our invitation. Actually, to brief the biodata of K.S. Rao sir is a very, I would say it's a very hard duty for me, because I consider, because the sir's biodata, as such, I think that no introduction is needed to such a great personality, but still I will have some of it. Professor K.S. Rao sir, after receiving his MTech degree from IIT Kanpur and PhD from IIT Delhi, joined as a faculty of civil engineering at IIT Delhi in 1986. His academics and research spanning over 40 years has been on engineering behavior of rock mass, stability of slopes, underground structures, foundations, numerical modeling, and seismic hazard, and microzonation of mega cities. An established teacher, researcher, and active consultant, Professor Rao has supervised 25 PhDs, 180 MPhD theses, and currently guiding more than 40 doctoral students. He is a recipient of IGS, Professor Leonard Best PhD Thesis Award, and Diamond Jubilee Award, and 20 other IGS and ISR entity Best Research Awards. A prolific writer, Professor Rao has published more than 350 technical papers in national and international journals and conferences. He has been the principal investigator of more than 12 sponsored research projects. Professor Rao designed and developed a large-scale polyaxial facility, static and cyclic direct shear apparatus, impact and creep testing facility at IIT Delhi. A large-scale direct shear testing facility for mined up material was established as CNPDI Ranchi under his technical guidance. Professor Rao is an honorary fellow of Indian Geotechnical Society and contributed extensively to the growth of IGS for more than 25 years in various capacities. Professor Rao has been the editor of the Indian Geotechnical Journal and IGS News. He was the president of Indian Geotechnical Society and president of Indian Society of Engineering Geology for the term 2011-12 and 18-19 respectively. For his overall contributions, he has been awarded the Lifetime Achievement Award in 2016. Professor Rao delivered the 41st IGS annual lecture and received the Kuckelman Award for the year 2020. Professor Rao provided solutions for more than 350 consultancies in the areas of soil, rock, and earthquake geotechnical engineering. His recent geotechnical modeling work for assessing the stability of the Chenab Bridge abutments has cleared the way for the construction of Jammu-Baramulla rail link of national importance. He is the consultant of Rohtang, Zadmorth, and Zojila tunnels. He is an extensively consulted for landslide and other slope stability issues of Chardham Road and rail projects. So, sir, once again, it's a great privilege to have your august presence on this Engineers Day. Sir, I hand over session to you, sir.
Okay, let me share my presentation and then I will start my. So, are you able to listen to me?
Yes, sir.
Professor Shah?
Yes, sir. Yes, sir. Clearly audible.
Yeah. So, very good afternoon to all of you. So, the Dr. R.K. Gajar, so the Major Dr. Sangvi, Professor Mehta, so the Dr. Shah, so the Professor Singh, and Dr. Madam Asha Lata, delegates and students and the invited guests. And I'm really delighted that you have invited me to deliver the Dr. R.C. Sonpal Memorial Lecture. As a student, so that I heard about Professor Sonpal and his achievements, and I never thought that so that I will be getting the honor to deliver this particular lecture today. And yeah, again, so the Happy Engineers Day. So this is another good thing is happening that say this lecture is being delivered on the Engineers Day. So I'm really, so the delighted. So as Dr. Shah indicated that there is a growing interest, so in rock mechanics in the LD college, and so they have been thinking of, so the offering a rock mechanics course in UG, and as well as, so the PG geotechnical engineering students. I think it's a good thing. So it is too late. I think most of the Indian colleges, so the by this time should have, so they get into the rock mechanics and rock mechanics related issues. So because of the fact that, say the huge amount of infrastructure that is coming up, so then in India, elsewhere, and you for the last 10 years, if you see it, so the Indian growth in the infrastructure development is mind-boggling, and be it roads, railways, and also, say the very long high altitude tunnels are being inaugurated and being constructed, and also a lot of underground structures which are actually coming up, and at the same time, say the very iconic bridges which are coming up, say the which requires, so the large foundations, so the especially rock foundations. So without, say the taking much time, I once again, so the thank the LD College of Engineering and Technology, and also like IGS Ahmedabad student chapter for inviting me to deliver this particular today's, so the lecture. Uh, as you know, like, so the by definition, so the International Society of Rock Mechanics, in way back in 1966, so that they have defined the rock mechanics is nothing but, so the theoretical and applied science of the mechanical behavior of the rock and rock masses, and it is that branch of mechanics concerned with the response of rock and rock masses to the force field of their physical environment in which, so you are getting the response to the force field of the rock and rock masses is what, so the being included, so the in this particular subject. So obviously the rock, and, say the you're applying the mechanics, because whatever, say the civil engineering structure, say we do it, either we are loading or we are unloading it. Loading and unloading process is resulting the, say the changes in the strata, whether you do the construction, on the rock or in the rock, or with the rock. So you will be applying, say certain mechanical principles, so thereby what is the rock response, that is what actually we should look at it. If we know and predict, say the rock response for the loading conditions, so then we will be able to construct, or we will be able to create the safer, say the structures. People are always having the thinking that, say the when we are able to do the constructions, say on soils, so any rock is, so is good enough to take care of the stability of the structures, but it is not really really not correct. So the rocks are more, so they're having the issues. So what I thought is, so the some amount of, say the rock mechanics and rock engineering part, I will be very quickly go through it, and then subsequently I would like to, so the look it into some of the projects, so the which we have been doing it. So as you know, like there are several applications are there. No, say we do the deep holes, say to get the geothermal energy, maybe 2, 3, 4 kilometers, say the down, where the temperatures are, say the high. We can exploit it, say that. So for that, obviously, we will be cutting through the rocks. Storage caverns, a huge amount of underground spaces will be created to store the oil or gases or chemicals. Even, so the off late for the military purposes also we do huge amount of, so the caverns. So tunnels are extensively being constructed in India, elsewhere, and the tunnels and other underground structures, say for the road, rail transportation, and especially for the hydel projects, say for diverting the water. We do construct head race tunnels, tail race tunnels, say in the hydel projects. And apart from that, say we have say the huge amount of issues related to the, whenever you do the expansion of the roads or the railways, so you will be cutting the sideways, so thereby you are creating the fresh slope, and these slopes are always vulnerable. Not only that, so there are landslides, so they keep happening, especially this part of that the year, when so that we have so the heavy intense rainfall. Slopes are so the are most so the vulnerable. So landslides, so the block movements, or the rockfall protections, so they're required for creating, when you create the slopes. So foundations, anyway, say the for the shallow to the deep foundations, especially for the buildings, bridges, and so the dams, you need to safeguard those structures. Small and large dams, especially for the water resources and generation of so the electricity in hydro plants, so the we found so the basically on the rock formations, but it is not really all the time, so we get the good foundation material, so thereby a lot of challenges. And apart from that, so the what do you do with your nuclear waste that is being created, so due to the electricity production? So nuclear waste is dangerous. You cannot actually dispose of so at any location, because the half-life of this waste is runs into thousands of years. So thereby you create so the very deep cavities, maybe 7-10 kilometers deep. You put that so in the canister and surrounding with a layering system, so that so the permanently the nuclear waste is so the buried underground. And yeah, one needs to find say the what is the suitable say the rock formation which can house these the facilities. And you do have the deep cavities and the shafts, especially the whole underground mining, for which say we excavate and we create uh, uh, the mines to extract say the economic minerals. So not only for the minerals, say for the military purpose also, so we do, and many more applications are actually there for the for in the rock mechanics. The content of my lecture, I will be briefly touching upon says some of the latest developments. The they are necessary to understand and do engineering with the rocks. So intact rock behavior, anisotropic rock behavior, weathered rock behavior, and behavior of the rock mass, jointed rock, so the under the uniaxial compression and the polyaxial stress state, uh, and also like say the understanding how material is actually the going to give away under the loading conditions. So that is fairly the brittle failure and interlocking of the crystalline materials, and also the shear strength behavior of the jointed rock play so the very crucial. If you understand the shearing behavior of rock or the jointed rock, so then you can do a better engineering with the rock. So the creep experiments of rock salt for the underground structures, we will look at, and then also in the Himalayas we do have say this problem of squeezing of rocks under certain loading conditions. So those issues are also we will. So these are all say the fairly the latest developments that are taking place. Especially so the IIT Delhi is pursuing rigorously several research scholars, so they put up their hard work, so that to create the beautiful rock engineering activities. And once you understand the material under the different loading conditions, so probably you will be able to do the engineering. So for today, I will discuss, say the 4 cases. One is, say the China bridge, the iconic bridge which is coming, and then this is going to be the highest bridge in the world, and then the Subansiri Hydel project, the powerhouse slope collapse uh, is very significant. So the engineering, so the feat. Subansiri itself is, so this project is 2000 megawatt, first time in India. And Rohtang tunnel, that is very much, so in the news last year only, the Prime Minister inaugurated Rohtang tunnel, has certain issues. So how we are dealing with those issues, say for this particular tunnel. And also, like Dr. Shah has indicated that, say that we have developed the world's largest direct shear box, recently established at the CMPDI. So that is for the coal dump, say the stability. These are the 4 cases I have just picked up, say that to highlight so the importance of rock mechanics and rock engineering. As you know, like, so I loaded, so the large number of slides, so indicating that, so I will be briefly mentioning it, and, say a, a common, say the delegate, so they will be able to get, say the sense what I am talking. Not exactly, I'm not actually going to teach, so the every bit of the detail. I will be just grossly covering the area. So rock, so the whether it is a in our engineering geology course, so that we study rocks are, so the you have the igneous rocks, volcanic rocks, so then sedimentary rocks, and then metamorphic rocks, and then they have their own process of formation, and they have their own, so the attributes are there. All rocks, so when they came into being, so the fairly they are intact. Intact is, so the no joints are there. As for the definition, so the earlier I said that a intact rock, so the on which the force field is applied, so then the rock may be having the joints. So one single set of joints, 2 sets of joints, many sets of joints, and highly jointed rock mass. So if it is highly jointed, so then we say it is a jointed rock mass. And then whereas, so if it is a undisturbed, so the material, so then we say it is a rock. So obviously the rock is, so is going to be very high strength, no issues, so the its stability is concerned. But, so the rock masses, so they do have the issues. As you know, like, so the bedding planes, the joints, faults, the shear zones, or the fractures, discontinuities, weathered zones, all these things, so that makes the intact rock, so the very weak. You see that, so the as if, somebody's cut that, so the in a planar faces, so the 3, 4, 5 sets of, so the joints, you may be seeing it in the good rock. And sometimes, rock like the schistose rocks looks like this. A lot of mica is actually the packed up, and when you do the engineering, say with that type of material, you have the issues. Here it is, say from Maharashtra, you have a Deccan traps are there on the top, very competent rocks, but below that, say you have the red bowl, which is, say, a very plastically formed, say, due to the volcanoes. So if you have such type of variable materials, and if the tunnel is actually the going off of it, so through the rock, and off of it, say through this, then you do have a lot of, so the issues. So the many times, so that we see, 3 sets of joints are there. Here also the 3 sets of joints are there. Rock is having a lot of friction. So that is the reason why, say it is not really sliding. But otherwise, so they're all jointed. when there are three sets of joints are there, why this block is not actually the coming out? So there is so much of, say the interlocking is there, so in the rocks. So you see that, so the how regularly, as if somebody is cut with a knife, so the joints will be like forming it, that way. These are not that originally, say the rock is came with these joints, so from the beginning. It is, say the solid rock is actually the subjected to the force field geological stresses, acute geological stresses acted. So thereby you get, say this type of 3 or 4 sets of, say the joints will be there. Now let us see it, say the in underground, so if you are doing a tunnel, the surrounding material is rock. That rock is not, say the is not solid. It's not intact. It's having a lot of joints. So if you have the joints, so obviously how the joints, how intensely the joints are, say they permeated in the rock, that will decide, say the whether this cavity is stable or not. So thereby intact rock with the discontinuities is what, so the you will be dealing with. That is the rock mass. That is the rock structure. Then inside, so the you have, say the three-dimensional stress state is there. In the mechanics we study, say there are principal stresses. There are the 9 stresses, out of which, there are 3 principal stresses, sigma 1, sigma 2, sigma 3. Either you call it as a vertical stresses or horizontal stresses. So the stress state, so inside is 3-dimensional, but we convert that, so the into 2-dimensional problem. So most of the time, in civil engineering or in the engineering, we 3D scenario we create, so into 2D. So what is that we do is sigma 2 is equal to sigma 3. So thereby you have the horizontal stress same in all the 2 directions, and then you have, so the sigma 1 is there. As you know, like, so the stress state is having its own direction. It is not necessary that all the time, so it is vertical and horizontal. It could be inclined, so they as well. So this stress state is going to influence, so the stability of the cavity, the shape of the cavity, the size of the cavity will be influencing it, so by the stress. It's apart from that, so the, as you know, like, so we do have the underground water, and the water will be permeating, say in these joints. The joints will act like conduits, so thereby the pressure or the pore pressure, say in the joints will increases. Then obviously the strength of the material is going to decrease. So it is the interplay between these 3 parameters: the structure, the instantaneous stress, the pore fluid. You need to understand, you need to comprehend it, so if you want to do a project. So there are several testing methods are there, so that to do that. Say this is a simple uniaxial compression, and this is a direct shear. You apply the normal load and you shear it, so that the material is going to shear along this. So thereby you will be getting the interface, say frictional properties. Or you are applying it, say a hydrostatic stress in all the directions, so that you have the stress is same. Here, say you have the horizontal stress is same, sigma 2 and sigma maybe 3, and you have the sigma 1, so the vertically. Here it is, so the different. So what we call is a polyaxial, uniaxial, triaxial, or the biaxial, or the polyaxial, say the conditions in which, say the material is, so the is existing it. A typical, so the stress strain curves, if you see it, it will be there, and it is a fairly the linear part, and then, say the peak, and after that, it is collapsing it. That is what we do it, so the in the simple uniaxial compression. If you allow me to discuss this, let us see. This is this curve is not, this curve is, so this curve is nothing but so the failure envelope. See, like so the normally we use the Moore Coulomb equation or something so the to give you the relation between the sigma 1 maybe say the sigma 3 are in different the form. So what you will be getting is when sigma 3 is negative here, this is the tensile strength of the material. Rocks do have say the tensile strength, so thereby assessment of tensile strength is important. And that this is sigma 3 is 0, so thereby sigma 1 becomes sigma c, so that is the uniaxial compressive strength. And then anything which is positive sigma 3, then that becomes say the triaxial state. Okay. So similarly, like say for getting the tensile strength, for getting the shear strength.
Okay. Participants, I think there is some internet issue at their end. You please be remain in the meeting. Sir soon will going to join.
So now serious. First you session and then now systems.
Are you able to listen?
Yes, sir. Yes, sir.
Okay, and some disturbance has come and then thereby disconnected. Uh,
It's okay, sir. It's okay.
Just. No, okay. So probably the lithological composition, so that we will be able to get these methods. So and then similarly the physical properties for the any material is so they're very important, and then so that we do the mechanical test. So we can do it so the using the wave propagation, dynamic elasticity, Poisson's ratio, bulk modulus, etc. You can get it, but so the normally we do the static tests. So that means so that directly samples will be subjected to the loading. So you can do it so the time dependent and time independent. As you know, like so the most of the time so we will be doing we'll be doing time independent. Time we never consider say the most of the time say engineering say the assessment of the material. So we can do it in compression, we can do it in tensile, we can do it say in shear to get say the different say the elastic constants. So similarly for certain materials, I'm going to project say the one such material which we have done so the testing taking the time into consideration, say like creep tests and the relaxation tests will be conducted say with reference to the time. So I said that so these are the L by D ratio, that is the length by the diameter of the specimen so that should be followed so the as stipulated so they as indicated. This is what actually this is a original rock say the red sandstone. If you cut it into different say L by D ratio, normally we use it L by D ratio 0.5 for the Brazilian test to get the tensile strength of the material. This is the point load, another strength index. These are so the L by D ratio 2 specimens so we use it say the for the uniaxial compression and also the triaxial so the compression. So for measuring the strains, so both lateral and axial strain gauges will be attached to this, and then that will be get connected to the circuit, and then thereby we will be able to get the stress, corresponding stress versus say the strain. Both axial and diametral strains we will be getting it. Also, whenever you do the testing on the materials, you should define like what are the conditions in which so that you are doing the test. And sometimes so the rocks do have so the lot of anisotropy, like you have the shales, phyllite, schist, gneisses. These rocks having some layering system, some beddings, so that will affect so the strength in different directions. So the same rock will be displaying the different strength. Obviously you should know like say the what is the orientation along which you are doing the test. So these are the physical properties. So the rate of loading of the machine is also very important, and whether you are working on the saturated sample or the dry specimen for getting the strength, that is important. Or whether you, because sometimes say for certain certain say the requirements, we will be doing the expose the rock so the at different temperatures and try to find out say the what is the strength. Similarly, the confining pressure in triaxial test, we always say the low to the high confining pressure as per the requirement so that we do it. What you get say the stress strain curves. If these stress strain curves, this is the axial strain and the diameter strain, this is the stress. Obviously for these are say for the sandstone, you will be able to get say the at 50% of the ultimate load, you can find out say the what is the load or the stress and corresponding say the strain. So thereby you will be getting the modulus values and Poisson's ratio. When you do the triaxial test so you will be doing it at a different confining pressure. So that means the specimen is subjected to a particular horizontal stress. Under that so you are applying the actual stress. So as the confining pressure improves, so the strength of the material is going to improve. So thereby all your elastic constants are also going to be. If you see it, say this is sigma 1 versus sigma 3, it is a failure envelope. So we know it, say the what is the at what confining pressure, say the what could be the strength. This is very important. Like when you do the any project, so the on the rock, as a civil engineer, so the you are loading or unloading it. So thereby how the material is going to behave, you should understand it. Of course, there are some simple classification systems are also evolved. So if you have this, say a failure envelope, how do you capture the curvature? Because you may do the test at low confining pressure, but if you want to do it so its prediction, you may not be able to do the test. So thereby you can predict it. So this is one of our say the simple theory, that is the you can use in any confining pressure what could be the strength. By knowing it, say the if you know the sigma c is the initial simple test, that is the uniaxial compression, and then say these two constants, if you know it, so that you will be able to. So with a lot of say the testing, what we found is say the all the rocks, whether it is igneous rocks, arenaceous rocks, argillaceous rocks, they do have say the alpha value 0.8 is virtually the constant. Only the B value is changing it. B value for the low strength rocks, so the B value is starting with 1.8, and it is going up to say the hard rocks, so the 3 or so. So if you know the rock type, you will be choosing say corresponding say the value of the B, and then thereby at any confining pressure so that you can get the strength. See this so these are the anisotropic rocks, like as I said, that shale, slate, phyllite, schist, gneiss, and some bedded say the jointed rocks do have this type of say the lines. If your loading direction is this, and what is the angle that is making, that is the B from the 90 degrees to 0 degrees. If you change the direction, So the strength of the material is changing it. You see it here, and it is 0 degrees. So the 0 degrees means what? The planes are vertical and the loading direction is also vertical. So thereby it is having say that particular strength. And here also it is 90 degrees. It is also having the high strength. But what happens here? So when the inclination plane is so the making 30 degrees, so then it will be the lowest. You see that most of the Himalayan rocks, where most of the tunnels are actually being made, they're all anisotropic rocks. So taking the which one you have to take the strength, either this value, this value, this value, this value. It all depends upon say the what is the position at the site that is more important. Similarly, like say these are tested samples for getting the tensile strength, point load strength. So point loads, tensile, or say uniaxial compression. So these are the fundamental say the properties of the material. Like soil mechanics you all studied, so you do the lot of tests, say liquid limits, plastic limits, grain size analysis, compaction, consolidation, etc. Similarly, the rock is also so the should be evaluated so the for its behavior. And sometimes so the rock is very sensitive. Say this is a oil shale. So when you are transporting the material so from the field, you should take a lot of so the care. Also, we do a lot of so the investigations so the exposing the rock at a different temperature. You see that so this is at 100 degrees, but whereas this specimen is so the 800 degrees. If you expose so the shale, which is a gray color, but because of the oxidation so they at high temperature it changes, and also a lot of inherent cracks will develop, so thereby the rock becomes weak. So for us it is very clear that so the as the temperature so the goes higher and higher, the rock is actually going to become from brittle to the ductile. So these are some of the samples which tested again so the with variation of the beta. So what is the the failure so the curves. So so the lowest strength is actually exhibited by this. So as we said that so it will be always happening at 30 degrees. 30 degrees you will be getting the lowest so the strength values. So failure envelopes are also indicating the same. So these are the basic things so which we need to perform so the tests on the specimens and for the engineering use. Apart from that so this is the confining pressure sigma 3 and sigma 1 minus sigma 3, that the deviate stress, if you do it, you got a failure envelope. Materials say that at low confining pressure their behavior is brittle. Their behavior is say they're brittle, and so as the higher and higher confining pressure increases, so they become say more ductile. So so you see that so the curve is actually become virtually the asymptote, and so it is not it is gradually so the bending. So because the transformation of the material so they at high temperature and high pressure, if you are exposed so then their behavior is so the ductile. Many times so the people keep asking say this material behaves like a brittle, or the other one is so the behaves like a ductile. No, it's not. Material is not actually the has so the any behavior. It is only the conditions under which that material is actually going to change. So these are, I'm not going into the details of it. A lot of literature is available. If you want, I will put up so there's some references as well. So these are the predictive models. Means you do some minimum tests, and from there so the how do you predict so the at unknown so the at unknown pressure or the temperature, what could be the rock behavior. So that is what actually so these slides are actually indicating. The next thing is so the rock is say the weathered. Like when you travel you see it say sometimes rock is very fresh. In other locations say the rock is highly weathered. If you see it say this is very fresh rock, maybe take basalt, commonly occurring, say the rock in this region. So you have the basalt unweathered, but the weathering is keep, so the increasing it. So weathering stages, W1, W2, W3, W4, W5, W6 is virtually, residual, say the soil. So don't you think that, this will have very high strength, and as the as the weathering is is increasing it, degree of weathering is increasing it, the strength of the material is also going to decrease. So we did, so the extensive investigation on Maharashtra area, because you have the volcanic rocks are there, basaltic rocks are there, which are supporting, say the huge amount of structures. You see that, I just wanted to give the glimpses of, say the what is the way we comprehend, say the material behavior. So this is W0 is, so the unweathered or slightly weathered, but as the weathering proceeds, so the it will be more weaker and weaker, and these are the different envelopes, so the see, the India is a tropical country. We have the high rainfall and high temperature. If high rainfall and high temperatures are there, so the rock is actually going to get subjected to the chemical weathering. So most of the classification systems which are there in the rock mechanics for the design, I will maybe explain it slightly later as well. We proposed, so the a separate rock mass classification system. It is a rating system, means rock behavior is captured in terms of numbers. Being engineers, so that we always play with the numbers for the design, for estimating the bearing capacity or estimating, any strength, etc. So thereby in rock mechanics, make the certain observations of the rock in its, say the disposition, and then try to give numbers, and then thereby the summation of number, so the will give you the rating. So the rating is, so the very useful. Let's see, like, so the rating comes, so the RW I am calling 100 to 81. 100 means, so the first class good rock, fresh rock, and whereas, so the weathering proceeds, so the rock rating is going to go down. So if the rock rating is, so the going down, don't you think that, so the its behavior is, so engineering behavior is, so the very poor? It is so. So again, say these are the, if you know the rating, you will be able to get its, so the behavior under any confining pressure conditions. Okay. Then, so the rock will be in a different, so the condition also it may be. So much of research has actually gone from the beginning of the rock mechanics. That is about the jointed rock. I said earlier that force field acts, so thereby the rock becomes, so the jointed. That type of material, when it is subjected to, so the uniaxial condition, what happens? You see that, this is, as if somebody is actually the cut along this very regularly. This is one set of joint, then you have perpendicular to the another set of joint, and then the face which you are seeing it flat, so that is one face. So thereby three sets of joints, so they are mutually 90 degrees, so thereby becoming, so the some sort of cuboid scenario. So these are joints. How this, this type of material is going to behave? This is one set of joint, this is another set of joint. So then, so it is making theta angle, it is having the h and the b dimensions, and then here this particular set is not continuous. We always do the staggering in the brick wall. So same way, in the nature also there is, say some amount of staggering. This staggering is actually making the rock, say the very nicely, say interlocked, so thereby providing, say the lot of strength. So we do this type of, say the, because in the on the actual rock you won't be able to do the test. So thereby we can, say the create this type of scenario through these modeling and then subject them. So this is what we call is a physical modeling. So physical modeling at different variables of, so the theta and s, that is the staggering, and then so you have the theta, the main joint, so the inclination, if you change it, and also the individual blocks so they are having the different configuration. Why it is required? It is required so the in the nature you will be having it so the variety of these scenarios. So these experiments are very the complex experimentation. You see, like making one sample, we will be using it say 350 blocks. How do you manufacture say these blocks and assemble them and then make them say the test it? Yes, we do that, and say the initial cutting of a particular material, selected material, and then say this is the model, this is the model, and this model is actually so the fixed with all the LVDTs and the dial gauges, so that so the deformations we will be getting it, and we are applying it so the uniaxial so the loading. So the system is looks like that. Okay, so when we did the testing on variety of say the jointed models, to our surprise say the sometimes the material is failing in splitting, in shearing, rotation, and sliding. These are the four variety of mechanisms we see it say the failures of the rock slopes. Like whenever you see a rock slope is actually the failing, it maybe splitting through the rock, or shearing along the joints, or say the rotational, or maybe say the simply sliding along the joint planes. So thereby with this experimentation so that we are able to capture the failure mechanism. Once we have the failure mechanism, we can capture the stress strain behavior, and we can also explain say the through a suitable theory, that is the joint factor so the theory, how strength is actually going to vary. Since so the time is the main constraint, I'm not actually going into the full details, but for each mechanism of failure you have a separate equation. How do I get jointed rock strength? How do I get jointed rock say the modulus of elasticity? Can you imagine that without doing the test, getting the modulus of elasticity say the of the jointed rock, it is a very difficult thing that could be so the possible because of so the development of these these say the test methods. Now if you see it, you heard about the shearing, rotation, sliding, splitting, etc. But when do you get these say the mode of failure? We keep commenting so okay, material failed, it is failed in shearing, it is failed in rotation, it is failed in so the sliding, etc. No, as I said earlier, material is not doing anything. It is the joints so the in which the material is actually the staying. So the conditions are actually going to fail the material in shear, rotation, or sliding, or splitting. So which are the parameters which are contributing for that? So the important so the joint, the critical joint, that is its angle is important, and then say the interlocking parameter which is actually there say that is, these two are actually going to define how the material is actually going to the fail. The mode of failure is not the material property, and it is due to the theta is this and the interlocking so the among the blocks. So we did a lot of numerical modeling as well, and then so they extended these theories so the to design the foundations so the shallow foundations so the for the rock mass. Okay, that is uniaxial we have seen, but what about say the biaxial and the polyaxial? This is much more complex because some of the let's say like tunnel. A tunnel is an opening in the rock, so obviously you have the side pressure is there, vertical pressure is there, but then along the axis of the tunnel, so that is so the zero. So you call that so the sigma 3 0. So you have sigma 2 and sigma 1. So that is a biaxial. But in some engineering problems so the all the three directions so you have the loading, that is polyaxial. Sigma 1 is there, sigma 2 is there, sigma 3 is also there. So obviously, say testing, if you do it, so the in this and see its relevance, so the for your project, and then accordingly, so pick up that, say the the strength. So, but for this, so I need an equipment. See, earlier I did, so the similar model, uniaxial, but I tried in the beginning, so the a biaxial in this direction. I calibrated springs, I put it, and then so the maintain certain amount of so the pressure. Of course, perpendicular to this face, sigma 3 0. So it is some sort of biaxial condition. So it is good. It worked well. Definitely, so because of the restraint, so the strength of the material is gaining it. So that means the effect of sigma 2 is there. But this is not enough, because when it is failing it, say these flanks, so the are deforming it, too much. So thereby I need, say a more robust. That is the necessity of designing a biaxial frame. So we did this. So Tiwari is, so the is one of our research student, say the who did PhD in, so the on this he designed it. So this is for sigma 2, this is for sigma 3. Under that loading, the specimen is, so the is applied the vertical load. So these are the different, so the full equipment in our rock mechanics lab, so it looks like that. Same model, same three sets of joints are there with, say the staggering and the inclination theta. And now you subject it sigma 1, sigma 2, sigma 3. And apart from this, so the variety of other cases are also have been, say investigated. So thereby a very comprehensive study that has been actually done under the uniaxial condition, biaxial condition, triaxial condition, and true triaxial. True triaxial is the polyaxial. So what is that, so that we are looking at? We want, say the what is the effect of sigma 2 on say stress strain response, failure strength, failure pattern, failure strain, deformation modulus, etc. Because these are, say the design inputs for any major project. So we need to know it. So it has been done, say very comprehensively. And just to simply, say the say to our surprise, say that we again, say that we got the failure patterns, which will be controlled by the conditions. What is that condition? So that is, so the ratio of sigma 2 by sigma 3 or sigma 3 by sigma 2, and then the critical, say the joint. So if you vary this, the material is going to fail in some places, some conditions, strain softening and strain hardening, and then, say the plastic behavior. So far, so we have believing that, so it is the inherent character of, so the rock to behave, so as a strain softening or a strain hardening. Most of the time, so the numerical persons, so they assume, okay, I'm assuming for the material, say strain softening behavior, and then, so they try to do the solve the problem. It is, there is nothing to assume, so in this it is not the material behavior, it is the behavior of the material, because, so we have created such conditions. So you change the conditions, so then the material behavior is actually going to be. So when do you get, so the material behavior is strain softening or strain hardening or plastic? Now the chart is actually going to give us very clearly, so the when the material behavior is going to be in that particular fashion. So it has actually given us, so much of confidence to define the material behavior, and thereby, so they created, say the biaxial, polyaxial, say the strength criteria. These strength criteria, so they will be very useful to predict unknown things, because you do some testing, simple tests, and based on that, say through a criteria, you try to get, say at much higher loads, say the how it. So I'm not really going into these details. So the more column, Dr. Prager, and then say we ourselves say they proposed a strength model say the and then whose so the envelopes are actually going to be that. So you have the deviatrix sections as well as so the meridian sections. And apart from that, so we did one more thing. See, during this test, normally when you do the brittle material testing, you go up to the peak. After that, say the post failure behavior, you won't be able to capture it. Why? Because most of the time, say we do the soft testing missions. If you have a servo controlled testing mission like MTS, etc., then you will be able to. So you have the full so the stress strain curves up to the residual so the state. So what is this? All are so the this is so the elastic limits or elastic behavior. So you join it so with a line, and then this is what peak line. So that is the A line. This is the C line. The B line. B line is so the after the failure, the rock the failure the failed sample is so the virtually the strains will become so the asymptote. So thereby you take this. So if you get so the slopes of this under the different so the loading conditions which looks like this, so you will be able to get the modulus. So in a way I always say before peak the real state of material is not there. It is already broken rock, like any field so the project you go there are all joints are there. So joints are there means so the material is so the post peak. So the post peak means so the how do you get so the modulus of the material so the after the failure. If you can define so the after the failure, so then you know something. Then there is another wonderful thing so the we thought that like see a crystalline rock. What is the crystalline rock? Like so the most of the igneous rocks and some of the metamorphic rocks, they are good crystalline rocks. If you see the crystalline rocks so under the microscope, there are individual so the minerals are there. This is made of so the 5-6 minerals, maybe quartz, feldspar, and so you have a you have some so the micaceous so the minerals are there. So pyroxene, amphiboles, see, these are the 5 minerals normally will be there. But what is the relation between these grains with adjacent ones? There are no the fudging, there are no cementing so that is happening it, but still we see it so the granite is a very good solid rock. It is happening it say because these minerals are actually the coming from the melt at different temperatures. So some minerals which are actually forming at so the at high temperatures, the others are actually forming at low temperatures. Because of that, 3-dimensional interlocking is actually the happening it. That is the reason why materials are so the are solids and having a lot of strength. So it is a micro level property. We wanted to experiment so that to understand its full behavior in a macro. Sorry, this is so the it should be a. So it is a micro. Normally when you do the modeling, what you do is the joints big, so they are big in the field. So but you do it so the in the lab scaling down. So a macro feature is being so the converted as a micro level, and then you do the testing. But here I am doing the reversing it. It is a micro level feature and I am making it so the macro level. How can I do it so the a quartz, feldspar, mica, pyroxene, amphibole, which are actually components of this particular rock. So I need to have the compressive strength of the material, pure mineral, and modulus and Poisson's ratio. If those values are there, I will be finding it so some equivalent material which will have the same proportion and so the same elastic properties. So this modeling is so is terrific because it's very, very difficult. So what we did is normally for the modeling so we use the plaster of Paris, but so the here so the what we used is is a dental plaster of 3 varieties and created some 68 combinations to create these, so the models. So these are the different models which we are, simulating the natural rocks which existed at the micro level, and we are making into macro level. Only thing is we are not able to imitate the grain boundaries. Here you see it, so the all grain boundaries are, so the you have the either the columns or beams, and the contact between the grains, so the are plane. So this is the setback for this, but otherwise, so the it is a great study and subjected to the biaxial, testing frame. You see that this is one representing, so the one rock. So several tests have been conducted, and we redefined the brittle failure. How the brittle failure is going to initiate it? Because in this you have, so the very low strength minerals are there, high strength minerals are there. When they are part of, so the a rock is subjected to the loading, how it is actually the which one is actually the going to initiate the cracks. So that is what actually the defining here. It is a very a major contribution, so the to redefine the brittle materials. After that, we started working on, say the how do you explain, say the variation of the strength. So we need to express, say the so what we did is, say the columns and the beam theory of which is existing, say in the structural engineering or the structural mechanics. So that has been actually the utilized. Two variety of short solution and the long solution has been actually the found. Basically the strength of the material is a function of, we know it earlier that, so the tensile strength or the strength as well as, so the modulus, but now we are actually they added one more elastic parameter which is missing it, in our understanding. This is the interlocking parameter for the crystalline materials. So thereby we gave, so the the equations for that. To our utter surprise, so the when we try to find out what is the K value. What is that K value? I said it is an interlocking parameter. It is not the strength. Don't assume that K value will be higher for the high strength materials like granite, etc. No, here it is, see, the granite is having it, 0.0067. It is mathematically calculatable. That is what we did it. Okay, so the granite is here. In general, we believe that, granite is very hard rock. Yes, no doubt it is a hard rock, but the interlocking parameter, that is the relation between the adjacent grains, so there will be, it is not, so that great. Once the granite is broken, it is forever, so the broken, it never, so the again, so the jointed. But whereas you see that rock salt, it is a simple sodium chloride or the simple salt. The salt is having, say the high, say the K value. So this interlocking factor of the rock salt, if you see it here, that is very high in comparison with any other, say the crystalline rocks. So this fact is, so there is revealing us a great thing. I will be explaining that, so the later. So I said that the shear strength of the material is very important. Say the shear strength between the bedding planes, joints, faults, fractures, and shear zones. When do you require that? Underground openings in the jointed rocks, and most of our structures are actually done in the jointed rock. Stability of slopes, of rock slopes, and especially when you are doing the rock bolting, etc., for the stabilization, in that condition you need it. Or socketed piles, say the rock socketed piles, say if you are doing it, so you will be considering about that is the slope problem, and then this is the underground, say the tunnel problem. This is the socketed, say the pile problem. In the direct shear, so we studied in the soil mechanics, so simple. So you have a simple 6x6, so the centimeter square, so the box will be there. In that, you put the soil, and then you apply some normal load and you shear it. So thereby your shear plane is always, you know, say in the mid of it. So as you are applying throughout the test, the shearing is, you know, say the way perfectly planar. That is known as constant normal load. Throughout the test, you know, your normal load is constant. Fine. But what happens, you know, so when you have a joint is having the asperities or irregularities, and then you apply the normal load in the initial, and throughout the test, do you think that, you know, so that normal load is constant? It is not. It is not, because you have a wavy type of, you know, joint is there. This will be lifted up and goes down, up and down, you know, it be, you know, nicely it is indicated here. So once you start actually shearing it, your normal load cannot be kept constant. That is, you know, say the non-planar joints and reinforced joints will behave this way. This stands for, you know, say the constant normal stiffness. So what people say that, you know, so they have done the jointed testing on the jointed rock material. No, it is not. They have not really done it, because they don't know exactly what is that they are doing it. So there is always, you know, say an issue of doing, you know, say the direct shear test, you know, so the unjointed rock. So this particular facility, what you are seeing is, you know, say we have created, you know, say this particular facility to create the constant normal stiffness in the lab, and then under that, you know, so you are doing the jointed rock, you know, so the testing. So to begin with, you know, so we did different specimens of, you know, say you know, so with the plaster of Paris. You see this waviness, the top block, and say this one, and you apply the normal load and you shear it. So the variety of, you know, say the conditions we have. Not only that, you know, say in the nature, the joints will be having, you know, say some filled joints also, some gauze material. Its thickness is also can be variable. So by doing that, you know, so you will be capturing it, the shear strength behavior of, you know, say the jointed rock. Normally the pattern has actually given a classical, you know, is the tau is nothing but C becomes, you know, so the 0, so you have the normal stress, and then, you know, so you have the phi b, that is the basic friction angle, plus, you know, so the I is the asperity angle. But this pattern's equation is not, you know, so is not going to be relevant, you know, so if you are, you know, so doing the jointed irregular joints, or the testing on, you know, irregular joints, because once you start actually shearing it, so there is going to be the asperity degradation. So I'm not going again, you know, so how asperity is actually going to degrade, you know, so with the shearing. So that we will be we could capture it. So thereby we modified, you know, so the shear strength equation under the CNL and CNS condition. But that is in the static condition. So what about, you know, so the shearing, if it is happening in the cyclic, you know, so the cyclic, you know, so it is a shearing in the static situation. You have a peak, and then after that shearing. But then, you know, so the loading and unloading it, you know, so the going back and forth, you know, so you have the backward movement, forward movement. So this is the 4 stages, you know, it goes that way, it goes that, it goes there, and it goes that way. So if you do it, you know, so your asperity is going to degrade and the strength is going to decrease. What is its relevance? Its relevance is, you know, so very much. See the slopes stability issues, what we see it, you know, when these slopes are subjected to the repeated loading and unloading, cyclic loading, due to the earthquakes, and slope becomes, you know, so the weak, and finally it will give up. So we did, you know, so on natural rocks, as well as, you know, so you know, so the other you know, artificial joints which we actually created in the lab, and tried to do the test. But we need a profilometer, because we wanted to know exactly how, you know, so when before the shearing, what is the surface like. So we have to capture 3-dimensional, you know, say the coordinates. So thereby you will be getting it, you know, say the complete profile. This is the lower one, so the upper one will be matching. So this is the profilometer, you know, so that we have created and then so a cyclic behavior of the rock joint, so we will be we could capture. See, the black one is say the first cycle will be having it, all the asperities are actually the shearing it, and then with so many, after the so many cycles, obviously the failure, the shearing plane becomes say the smoother and smoother after 29 cycles or 30 cycles. So then it is like this. So this is a very complex experiment, and highly say the irregular joint will have that or the intact material, and then the rest of the cases so the fall between the planar joint and say the with the degree with the different so the asperities. So with this so the we could so the define the shear strength of the material so the very nicely of the jointed rock, developed a new direct shear facility, and further modified for the cyclic loading it, and extensive tests conducted, and developed a new shear strength so the criteria, and then of course so the used for the numerical modeling as well. Let me introduce so the another interesting thing which is not commonly done. This is the rock salt which I am talking about it. Say this is the, in the olden days, say we used to use a crystalline, say the salt for in our cooking. So this is the it is slightly rosy color, and in the Pakistan, so you will be Pakistan Himalayas, so you got plenty. Of course, India is also extension of that, so thereby in India also in the Bikaner, Rajasthan, so we will be getting this material, but slightly under deeper. But Pakistan is, so the world best rock salt, so the producing country. See this, it is a pure crystal, salt crystal. But how do I make, say the specimens, for doing any research on that? If I use it, so the drilling machine, I will be using the water. So, but the salt is going to dissolve. So most of the salt, so that comes from the Wagah border, so from Pakistan to India. Okay, so our researchers, so they went there and purchased, say the blocks, and these rock salt, so the specimens were made, say through the lathing, not drilling. So the lathe, so the in Amritsar, and then brought these so the specimens so that to Delhi for doing the testing. So we, as usual, like any material, you do all types of tests. In addition to that, these are the general properties of this rock salt. It's an excellent material, and we do so the SCM etc. You can see that so the perfect cubic crystals, and when you are loading it, so the how the grains are actually, the grain boundaries are actually the going to give up. This is the stress strain pattern. This material behaves very nicely. Loading and unloading, so you can do it, and still so the have that. So this is triaxial condition at different confining pressure. So as the strength increases. But this material, so we wanted to test it under different temperatures as well. So we created a chamber. It's a high temperature chamber around which so the heat is generated, and the sample is exposed to the 100 degrees, and then so the at that condition, so you try to see its behavior. Why it is required, so I will let you know later. So the effect of temperature, if you see it, low temperature, and so the this is at 25 degrees, this is at so the 250 degrees temperature, obviously it becomes more so the ductile. Apart from that, so this material is having the time dependent behavior. Earlier I said that time independent, time dependent. So now you see that so the time independent, I need to have so the creep testing facility. This again so the creep testing facility is designed, and so creep behavior is captured. So you see that so you put a constant load on the specimen for some time, and then so you keep measuring the with time say the deformations or the strains. Finally, the sample is actually the failing it like this, so some sort of bulging, and all the grain boundaries are actually the getting cracked like soil. So so the tensile failure is due to the significant bulging of higher temperature could be observed. And so this behavior is a very typical, and then that explained so the through the microscopic pictures as well. Now let us see, like say the what are the applications this rock salt is actually having. This is, you can take it as a case as well. We use it wherever we get rock salt deposits, so we can use them as underground storage of the oil or the gas. See, these cavities are the underground the cavities are so the very deep means so the very large dimensions, like 300 by 100 square meters, so the area. So you use it say for storing the gas, okay, or so the oil. And then this is wherever the you see the rock salt, so the this is indication of say the presence of oil, and of course salt production, and also like repositories for the hydrogen and ammonium and helium gases, so the underground you can create. And then this is storage of so the compressed air. And then this is the most important thing. I said that so the waste management, especially the nuclear waste. These are the canisters, highly radioactive waste that will be put so the in the nuclear waste. This is the rock salt so the cavern, and in which so the these canisters are put. If you do that so the what happens, let us see. So we did so the extensive modeling based on the leaching information, as well as the mechanical behavior of the rock salt. And then say we wanted to simulate these are the canisters which are actually going to be dumped under a deep say the depths, because this layer is say the rock salt deposit in which so this waste repositories will be permanently buried. So taking say behavior, if you do the prediction, let's say this is the canister size, your opening size is so much larger, okay, and then there is a white part is there, that is the gap. So what is going to happen so to this gap with the time, because the surrounding salt is so the creeping behavior, it is going to creep say with a particular rate. This is time t0, that is first one. So after 1 year, this scenario, 10 years, 25 years, 35 years, 50 years. 50 years, if you see it so your canister and the surrounding say the salt is say the completely closed. Once the canister is say the is encapsulated so the in the salt, it is forever so the it is so the will be there. Now so the I will comment on that. Earlier when I was doing it say the interlocking parameter, I said that so the rock salt got the highest. Now you find the answer so the why rock salt is say such a beautiful material for the nuclear waste repository, because it is having the highest interlocking so the parameter. I'm not talking so about the strength point of view. This is a softer material, but so it is having a time dependent creep behavior, so thereby it is very good. Another issue before I get into the cases. So the squeezing phenomena is very common in the Himalayan say the projects. Say the rock bursting, squeezing, and say the cyclic loading. You can do the cyclic loading, so thereby because of the fatigue so the rock is going to break. That is fine, the repeated loading. But what is these two processes are actually really creating a lot of problems say in the Himalayan projects. So the first one is rock bursting is so that happens when you have a very high in situ stress state, and thereby no cracks. The rock is brittle, and when you are doing a tunnel, so suddenly you are releasing the stresses. So sudden release of the stresses will leading to the sudden failure. Okay, that is rock bursting. A crack with crackling sound, so the rock is actually going to break, so when you are doing the tunneling. This is a major issue. And then there is another thing, say squeezing. Rock is good apparently, but then when you do the tunneling, so on the side slopes or the crown part of it, so it changes its behavior because of the squeezing character. That is the elastoplastic, so the deformation is going to set in. So initial stages it is elastic, it is good, strong, but then so after that so it is going to the plastic deformation. Excess plastic deformation is resulting into the finally failure. Can you see it here? So a tunnel which is already supported, but then it is getting squeezed inside, and then the rock, the tunnel opening is actually the getting closed. So thereby we wanted to investigate this, so the in a Rohtang tunnel. I will be talking Rohtang in different for the different purpose when I will be discussing so the case studies. But at this stage I've used so the data of the this particular tunnel phases. A very elaborate approaches they are there in that, taking into semi-empirical, semi-analytical approaches, numerical approaches which are there, say in the literature to predict, say the squeezing phenomena. So what we did is, so we wanted to revisit all these formulations already available. 64 sections. This is the phase when you are doing the tunneling. Say the what you see it, what type of material in what condition. So that is mapped a very exhaustive. So the mapping will be done, and also the classification is also made. This is a Q classification normally used for the tunnel supports. So then we did the numerical, so the analysis as well. And then ultimately, so we come up with, say the in 3 ways we can, say the do the squeezing prediction much better than, say the methods which have been, so they enlisted earlier. So one is the JF concept. So the other one is the Q. The another one is, so the N value. So that is, so the what we, so the finally, so they proposed it. So what I have projected is, so that we try to understand the material behavior under different conditions, the conditions in which the material is varying it, like say intact rock, anisotropic rock, weathered rocks, and then jointed rock subjected to the different loading, then direct shear, squeezing, etc. So unless so we know the behavior of the material, we won't be doing the engineering. So if I wanted to so the design a tunnel or a collapsed tunnel, say if I wanted to set it, so I need to know it, what is the surrounding material behavior. So without that, so we won't be able to, because the failure is already happened, and in such condition, so how do you do it? So with whatever the little opportunities I got it, so the almost say 390 cases of different, so the variety of say projects we did it. That has actually given us, say the strength to assess the rock well, and then so thereby we try to do so the engineering so the with that. So I'm taking it so the very briefly the 4 cases, and one is say the China bridge abatements, and then say the stability assessment of say the China bridge abatement, Subansari powerhouse stability, and then the leakages inside the Atal tunnel, Rohtang tunnel, and then again so the stability analysis of coal mine overburden dumps in India. So these are the 4 cases. Very briefly I will try to present it. This is so the across the Chenab. So this is the USBRL, so the project connecting Jammu to, say the your Baramulla. So Benihal to Baramulla, already the trains are running it. But because so this Chenab River is so to be crossed, so this requires so a great iconic bridge. Similarly, the tributary of so the Chenab is Anjikad. So here also so you need a bridge. So initial stages, this is a architectural so the view, but this is not the real bridge. So now the real bridge is almost getting ready. You also must be seeing it in videos and in the so the YouTube, a lot of information is available. So it is flowing down. I will be taking this particular case very briefly, and this is so the right abutment, and then this is the left abutment. There are so the viaduct part is there. So the train is actually going to come and so they go into the tunnel there, and it is going to come say through the tunnel. This is not the tunnel. So what is great about this bridge? So this is the particular project. So you have the Anjikad bridge, and so you have the China bridge is there. If these two bridges are actually done, there are so many small bridges and tunnels. So once that is done, so the Katra to Kajigund, you can so the travel the whole Kashmir, so you will be going through very nice so the scenic beauty. This is great. Now you see that so the Chenab, and so the once the bridge is actually made, this is the arch bridge, and from left abutment to the right abutment, so from this is almost half a kilometer, 505 meters distance. And what is the height? You put your Eiffel Tower, so in Paris you have the Eiffel Tower, say 324 meters height. That still, so the 35 meters higher than that. So from the bridge deck to the water level, it is 359 meters. That is the reason why it is going to be the world's highest bridge. It is a mind-boggling, say the you can see the pylons, say either side. The whole construction of say the bridge, say is done, say through these pylons. When I entered, so this was under controversy, and 2008, 2009, and they said that say they want to get the global stability, which was assessed earlier, but because of the controversy, I'm not going into those controversies, etc. So we need to establish it, so the global stability of this particular with a proper modeling of the rock. You see that rock is, so the exposed rock is actually having that. This is that, say the dolomite rock. It is having, say the J1, J2, J3, 3 sets of joints. This is very plain. And then this is, J2. It's a rough joint. This is further rough is, so there. If happens to be this joint, maybe the lot of friction will be there. But if you are, so your slope is actually controlled by this J1, so then you have the issues are there. So the modeling, what we have to do is numerical modeling using the U-deck and 3-deck, and these are the different modeling techniques which are so you must be familiar. In 2009, so doing a 3-deck and U-deck, it is a very rarest of rare, so the thing, and the modeling has to be done, so the by simulating, so the joint conditions. And also the loading, as well as say the seismic condition. As like say this area is so the highly seismic zone, so thereby we have to establish it the site specific so the information, and then based on that so you have to do this modeling. This is the 3D modeling. 3D modeling is so you take almost 200 meters of the hills, complete so the hill, and then so they start doing the modeling it. So the section looks like this, and this is a cut slope. So this is what actually the abutment the abutment pier is actually abutments going to be. The foundation for this is actually the mind-boggling 50 by 36 square meters. The main challenge is, so the how to get, so the parameters. So thereby we did, so the extensive research on, so the material parameters, not only the laboratory tests, but, so the extensive testing was actually done in the field. And also we created the drifts, and in the drift, so we have done the lot of tests. And based on that, so these parameters are actually obtained, and that these are the parameters which we need it for the analysis. So to cut the story, so the short, the factor of safety, so the comes up, so the fairly safe, and that this is the most important thing, that there are 75, so the conditions in which we have assessed this jointed rock. That means, full simulation of jointed, which are actually the present in the site, say that you need to take into account. Then the loads, then you have the seismic loads, and then, so the under the seismic, so the loads, what is the factor of safety, so the you get it. Now this is the bridge. So due to our studies, a lot of controversies, so we put to rest, and we have given the life to this particular project. We are very emotional about this particular project, and we fought against the so many people and even the courts, etc. And then finally, see we could win, because the winning is actually because of, say the correct assessment of, say the material and its, say the behavior under the conditions. If that is not there, so then things would have been, say the gone out of control. Now you see it, say the how the slope is actually the cut for the different foundations. So this is the abutment piers, so the P40 and P50 either side. It's a huge, so the foundations. So extensive numerical analysis, taking into account of discontinuities, monitoring points, so they at several places, not only on the surface, but, so the at 10 meters below as well. UDEC and 3DEC analysis revealed that the slopes are stable, and slopes are stable, but we want to make it, 10 times more stable. So thereby we suggested, say the suitable measures, rock bolting, weld mesh, and shotcreting, and also the providing the effective drainage system for the long-term stability of that. And also we are getting a great opportunity to monitor the slopes, so the so with the instrumentation. So the huge amount of instrumentation is actually the put in place, so that, we will be learning the lessons. So that is my first case. I think 2022 this China bridge is going to be inaugurated. So if they open the tickets, say please book it, because it is a great feeling sitting in a train which is going to go, so at a height of, say 359 meters. It is awesome, so the valley and the surroundings are mind-boggling. There is another great project, so which is coming up in the northeast, Arunachal and, say the Assam. This is that, say the Subansiri River. Subansiri River is a tributary to the Teesta. So the project is actually somewhere here, very close to both. This river is actually separating the states, and as you know, like, so it is highly seismic, say the zone. So that is the river. So that is the main dam going to be Coffer Dam, and diversion of the water for the construction. And then, so these are the HRT tunnels, so 8 HRT tunnels of different sizes. And then, so it will be coming, so the feeding the turbines. So this is the powerhouse. This is the surface powerhouse. So very compact, 2000 megawatt, first time in India. That project is actually the being built, in the Shivalik formations. Shivalik formations are very soft formations. And then, so if you see it, the 8, so the units, 8 into 250, so there were 2000, so that. So for giving the space, so for making the space, so the original slope is that, and a cavity, a opening was created. Means, they excavated. Okay, open powerhouse. So it is, you can see it, it is fully engineered and, say properly stabilized. So this is the scenario, 160 meters, so the height. These are the different HRT tunnels are already made, and then, say the powerhouse excavation is actually happening it. And suddenly this is what actually happened. The whole, say the slope came crashing it, say the and over a period. And say this is from the top, say if you see it, this is the first unit excavation, 40 meters below the below this, because this is the HRT tunnel first unit. And then another 40 minutes, say for the foundations and turbines etc. you are making it. But then so the rest of the 7 units, say completely under the muck, because the slope is actually the failed. Why slope is failed? It's a textbook, say the answer. A shallow shear zone is there, but which is undetected. Unfavorable jointings are there, joints which are actually the dipping along the slope, so they are unfavorable. But this common sense is not actually so the aware of it. Heavy rainfall and excess water. You see, water is always so the detrimental for the slope stability. So if you are not properly so the channelizing the water seeps into it, the rock becomes so the very weak. So soft weathered shivalik sandstone saturated so with excess water, and then obviously so its strength is actually going to be reduced. Stress relaxation. What is stress relaxation? You have cut 160 meters so the hill, and you might have stabilized it, but there is huge amount of stress is actually getting released because of the stress relaxation. So the warping will be taking place, so parallel to the slope, so you will be getting the cracks, rock wedges formed, steep slopes, dynamic loads. Not only the earthquakes, but so the on the top of the slope, so there are heavy vehicles, so they are parking and running around, so that creates vibrations. So that is also one of the reasons why the slope failed. Ineffective drainage system. So the mind you all, so the effective drainage system will so the not create any pore pressure in the slope, so slope will be stable. But your support system is not correct, and ineffective drainage system leading to the failure. So in any consultancy, when it comes, so your time is say precious. So the project people come only at the last minute, and then they think that so you have a magic wand with you, and IIT professor you have contacted, and then thereby he is going to set it right. It is not really correct, because you cannot do any investigations, and the slope is already so the exposed to all types of irregularities. And then thereby now so the to set it right, so that it is a Herculean task. It's the real challenge. So we did so the stage 1, stage 2, stage 3 analysis. I'm not actually going into the details, so they again variety of properties, combination of properties, we took it, and so we start actually getting the factor safeties. The first thing is so the factor safety, and the second so the column is your probability and reliability. What is the type of combination so the which gives you the reasonably so the properties, so that we have divided into so there's several case 1, case 2, case 3, case 4, and then we did the back analysis and then tried to fix the properties, and then so we remodeled the slope, and then also say created the required so the slopes, so stable slopes. So shotcrete definitely so there is important, and then the rock bolting. So we created the 15 meters so the bolt center to center 2 meters, and then so we used the wire mesh in different segments. What are these PS1 to PS8? I will let you know. You see this is the complete so the slope, and that this is the slope so which is failed. So that means the main part of the slope is so the totally came down. This is going to be the powerhouse base. So we divided into different segments. So this section is here, this section is so the here, this section is actually there like this. So now if you see it, so the here the shear zone is existing at. This is the shear zone. You have created the slope there, but then this is completely gone. It's completely gone, these are the pictures which are your HRT is actually the coming and joining there. Your penstock is actually the joining there with the unit, but the slope is so the already gone. It is not that easy. It is not that simple that okay, you just so the backward you push it slope and then create the new slope. That is not easy because this is a small area which is available. You cannot actually do a lot of so the maneuvering for this. But anyway, we did it. So failure mechanism and reasons were established. Design parameters obtained for the back analysis for the rock mass and the shear zone. Probability and the reliability concepts applied to account for the rock mass heterogeneity, and slide and phase 2 so they used for the assessment of the stability. Due to the presence of major shear zone, the flattening of the slope suggested. Combination of support system has been so suggested to achieve the required factor of safety for long-term stability of the subansary slopes. And this is very important. Many times so we do the shotcreting without giving any breaks. So we suggested the panel shotcreting 5 meter by 5 meter so the paneling we did it so that the slope is actually going to breathe. If you are closing the nose and the mouth, so the people will die. Same way the slope is also having the breathing. You should create the breathing capacity. If you are just closing like a blanket, so you put it over it, so then you will be having the problems. So the suitable catch drains, the PCC cover on the berms, and the effective drainage system were recommended so that the slope is so the now this it is rebuilt and the slope is so the functioning it so the perfectly all right. The third case so the is a case came into being it so the very recently. This is the Untitled Tunnel so the entrance from the south portal side. The main issue is so there is a Serinala which is so the over it, and it is feeding a lot of water, and then the water problem leakages are actually are there. This is the ice so the when we visited say the 3 months back. So Government of India, Ministry of Defense under the BRO made a committee to look into, because the Atal Tunnel was just so inaugurated by the Prime Minister so the last year, and it is 9 kilometers so the tunnel connecting so the Manali to the Leh. Sorry, the yeah. So 43 kilometers so the road journey has got shortened so the with 8 kilometers so the tunnel. It is a fantastic road tunnel. So somehow so that I happen to be the chairman of this particular committee, look into the seepages. So what is the mandate? Mandate is so the study and assess the major locations of seepage, and study to ascertain reasons for the seepage. Study suggest the remedial measures to the present system, and explore the possibility of can we divert this Serinala out of the way so that so the water will not be seeping. So it is a horseshoe shape so the high altitude tunnel, and above so the 3000 so the plus meters, 8 meters dia and 9.02 kilometers. So Manali connecting so the Manali to Lahore Spiti, and built with state of so the art EM systems, transverse ventilation and SCADA, so firefighting, well illuminated radio, telephone, FM, you name it, everything is actually there in this tunnel. The section looks like this. So you have a tunnel that in the base so the this is the ventilation slab, ventilation ducts etc inside, and then so you have the up and down so you have the tunnel section is there for the transport, and then below you do have so the Aggress Tunnel. Aggress Tunnel is a escape tunnel. So every 500 meters you have a a door in an accident, so you escape, say from this. And then below that, so you have the main drain is there. So the section looks like this. So the idea is, say the when you put, say this lining, so we will be putting the membrane as well. So there are several variety of arrangements which will take the drainage out. So this is on the day of, say the inauguration. It looks so great, so the a beautiful, so the in 8 minutes, so that you can cross the 9 kilometers tunnel, such a air conditioned, so with all the modern equipment and everything is actually there. This is the Aggress Tunnel. Aggress Tunnel is also, escape tunnel is also below, which is, so the also good. This tunnel is actually the somewhere in the tip of your Biaxial, so the valley. Actual thing is that, so there is a nala which is coming. It is having the 4 branches, but this is the Seri nala. Seri nala is from the top, so it is crossing it because the tunnel is actually the below. So thereby there is a since they are going slightly at a particular angle, so there is a this particular zone is having the problem in the tunnel. So on the top, so if you see it, this is the valley and it is full of ice, so during that time hardly you see it, see any flow coming. Okay, so this is the south portal side and then that is the north portal side. If you take the section, section looks something like this. So these are all, so the phyllites, cysts, and megmatites. These are all, alternately cysts and quasitic, so the phyllites, etc. Phyllites, cysts, so these are metamorphic rocks. So obviously they have a highly anisotropic behavior is there. So this depression, you see it. This is where actually the Seri nala is there. Seri nala is going, so along this, and then below that, so you have, so the what, quadratic, phyllatic, or phylite quadrate, so the cysts are there. So they are highly dilapidated because the water is actually the seeping through this zone, and so the highly weathered. Even when it was constructed, so the lot of collapses. So the tunnel was got, so they delayed for 4 months, for 4 years, so that because of, so the this issue. So the portals, we made the site visit, portals, tunnel, egress, all these places we have seen it, and we have seen, so the where the leakages are happening. Can you see it? So the earlier Atal tunnel diagram, the photo, and now it looks so shabby. So the water is coming, so through the construction joints. The BRO is actually doing it is their best, so to divert the water and wherever, so that they can take in this segment, so but forever it cannot be tolerated this way. So thereby this committee. So we did the inspected it, and then we gone into the full details of it, and then we examined, so what is the water quality that is coming. Luckily, so the good clean water is coming. No fines are actually moving, and the main drain, so if you see it, so the drain is actually running, so the awful. So awful means indicating that, so the drainage system is not, so the effectively working. Okay, first of all, let us see, like, so they measured it, 100 liters per minute. So thereby 86 lakh liters per day water is actually coming. So it is a huge quantity. It's a huge quantity which is actually coming through the tunnel, and 80 to 90% of the designed, inward drain capacity on, say the south portal site, and clear water is coming. No migration of fines is coming. And where do you get the leakages? So the contact grout, so the pipe leakages are channelized to the. This is, so the temporary arrangement that has been actually done by the BRO. So normally we look at the whole problem into 2 ways: the drainage provisions beyond the Seri nala, and the drainage within the serinalla. Okay, so this is the arrangement, so they have done it beyond the serinalla. There is no dimple drain which is so capture the water surrounding the tunnel. That is not there, but only the say serinalla, because this part is anyway dry, mostly it is dry, so thereby they are not provided so the any drainage say the arrangements. But here it is say the fully dimple drains are there, so they will be collecting the water and then they will be putting into the main channel. So the leakages indicate that the waterproofing membrane not functioning as expected in this particular region, unable to capture the water which is seeping through the tunnel. So thereby my first reaction is so the needs improvement. As you know, like so the Himalayan tunnels mostly drain tunnels. Drain tunnels means so the drainage will be coming, means water will be coming, the water will be captured and put it so the collected through the different drains, and then so they pass it to the main drain, so the main drain will take away. So thereby you can so the get away with less so the design capacity of the lining. Whereas so whereas so the if you are you wanted to do the undrain, means so there is no drainage allowing it, so thereby your tunnel will be so the totally dry. There is, but that requires so the you need to design the for the loads which actually the going to come on the. So drain tunnels, the undrained tunnels and drain tunnels. So Atal is the drain tunnel, so the drainage reduces the water pressure. Drainage is the crux. So if you are mess it up, so the provision of the drainage drains properly are not functioning it, then we will be having the issue. So the dimple drains, longitudinal drains, cross drains, pavement, and the main drains, so they are the provisions which are there. This is the system. I'm not actually since the time is actually the issue. So now in the serinalla section, so they have provided this is the first layer of so the shotcrete. As soon as you cut the tunnel, and then so you have the drainage membrane is there. That is going to collect whatever the water which is actually the coming onto that will be taken away and then put it into this main drain. So and then there are so the then this is the final lining, and then here also so the in the base also you will be having the cross drains will be there. So these drains are also will be leading so to the main drain. So I colored it here showing that you have such an arrangement of the drainage, but still so your full drain is so the not flowing full capacity, indicating that so your membrane is got choked, so thereby it is coming, the water is actually coming through the construction joints. So this is how actually the membrane etc will be done. So now my solution, the committee, what we thought that is okay, the construction joints which are actually the C-lay, you cannot actually do anything now, you cannot actually reconstruct or redo anything. So this should be properly so the strengthened and also sealed with a suitable say the chemical grouting, then relieving the pressure and the channelizing, whatever already the some measures are so the in place. So we are recommending that you continue with that. So you release the by tapping the water so the at certain locations, and but so the you close the so the all the construction joints from inside. This is the immediate measure, because we wanted to have a long-term measure. Long-term is reduction or the diversion of so the water from the serinalla. Whether serinalla can be diverted or not, that requires so the huge amount of studies. So thereby we put it under the long term, because the nalla is the valley is so the presently under the snow. So so this is so the leakages sealing and strengthening so that can be done through the chemical and the cement or the microfine cement grouting. and suitable grouting scheme shall be adopted. Migration of the water shall be monitored carefully, and required grout pressure, etc., worked out. And then the grouting should be started from the mid, from where you are getting, say in the tunnel, which drainage, to say south portal side, so that you keep so the improving it, and gradually you come to the portal size. Uh, then say the diversion of the Serinalla, see, that's a very tricky thing. We have so the scene, and so the worked out possibilities. What we thought, that 1 kilometer length of section where the water is actually seeping so the from the Serinalla, because Serinalla is a fault zone. So so what we thought, that from upstream to the downstream 1 kilometer further down, you divert so the water of the Serinalla through the steel pipes. So that requires so you need upstream so the some check dams. Desilting basin is actually the required, and intake structure so you need to create it, and then the piping so there should be, so some amount of civil structures are there. So that will be based on so the hydrological profile, and so the geotechnical investigations, etc. So the need to convert that work is actually now going on. So also we thought that so the maybe Serinalla zone waterproof, so that is on the sideways also so the you can use the waterproofing, and so the put the some sort of so the lining is and then with that also you will be able to reduce the water availability say on the in this particular zone. But this is so the fairly easy and workable. What you are fastening the water flow above over the tunnel, so thereby the tunnel is having the less. So let's see, like so the how these methods will be adopted so for the improvement. Now the action is actually taken, and they are working. The final case, I'm sorry so the I delaying you people, but so this is the last case. This is also so the very gigantic so the problem. Stability analysis of coal mine dump overburden so the dumps, so the in India. These are the black spots so they are the coal mines. So coal mines are always so the situated in the river channels. Because most of the time so the underground mines are not actually being operated. So it is the open excavation. This is the coal. And then so it is at a particular so the gentle inclination, and it is a forest area and non-forest area. So this is the comprises of say forest area, non-forest area, and then this is how actually the opening will be done. So it is excavated. So that means the top layer is getting scrapped, and then the coal is actually being taken. Coal available so the in seams. The seam thickness may be say 3, 4, 5 meters so the thick. That will be like a sheet so it will be, and then it will be taken. So these are the different stages. Whatever the material, extra material, coal anyway will be recovered, but the rest of the material so that will be dumped here. So like the material can be dumped so the external, or the material can be dumped so the material can be dumped so the in the internal dump as well. So let's see. So the dump height is actually going to keep on so the increasing it. The size of the material so in the dump is so the very large, even going up to the 200 200 or plus so the mm or so. Big blocks will be there so the so now you see that the coal is completely so they're taken away, and then after that so they will rehabilitate so the whole area. This is the technology they normally adapt. But these coal dumps, the mine dumps so which are created, they are big hills, so the whole area looks something like this. If somebody is actually opened the audio, I think. So could you close audio? Okay, so they are big mountains, but sometimes so they will be the slope stability instability will be there, and then they will be failing. And if these along with the rainwater, so if this material travels, and then they will be choking the river nearby, and then create so the a havoc, so the many times so the accident occurs, and many people so they die. So thereby, as per the mine regulations, so that you can go up to so the 120 so the meters high, but so the can we go so the higher than this? You see that so the stage by stage so they will be dumping it, and then angle of repose is actually the roughly say 38 36 degrees. With this so the angle of repose so the uh, uh, are we in a position to go? I don't want to read it say anything. The sum and substance is this type of material we never tested. You see, in your direct shear so that you will be doing it on a very small say the grain size so the material, not the big boulders, etc. So increasing rates of overburden generation so the in the open cast mines, increasing pressure on the existing so on the land to receive the overburden beyond initially designed geometry, and demand for the reclamation so the of the site, etc., is the major issues. So thereby and this is how actually the failure mechanisms will be taking place so the slope will be failing it so the in several fashion. And also the material behavior, if you see it so the here is on compression, it is the simple shear, it is the extension say at the top part. So that means the material is being say the subjected to the different mechanisms of failure. So leading to the eventually so the final failure, etc. So thereby what is that so the how do we get so the material properties when their sizes are actually the very large boulders are actually there? We have not done any testing, etc. How do you get your CN5 values, and how do you get so the under the loads how this material is actually the going to behave? So scale effects are also going to so the two questions primarily comes, does the particle size of the coal dump material matters, and does stress range on the dumps matters? These two questions really so the industry is actually so they're having it, but since the facilities are not there, so we could not really have a concrete so the answer to it. So we took it so that challenge, thinking that so the present 90 meters or 100 meters dump height, so can we raise it so to the 150 200 plus so the and beyond. So if you see it so a normal dump is so the having maybe the normal load is normal stress is so the around 1 MPa. If it is a 90 meters, that is what actually so it is recommended. But so the it is fine up to this level because it is less than 120 meters. So, but if the dump is height is actually the going so the much higher and higher, and this is mind boggling so the 350 meters so the high dump, how the slope is actually the going to behave. Unless you capture the material behavior, you will not be able to certain about it whether the slope is actually the going to be all right or not. You do it say small testing, and hoping that so the your the linear so that you project it so that you will be getting at that so the extrapolated values are going to be very high, but it is not. The material behavior is so the non-linear. As the grain size is actually the keep increasing it so the you won't be getting the envelope is not actually the going to be. So thereby you what you will be getting is say these reduced properties. How do you know it? How do you think that say that is certainly it is happening it? So this is the main say the context we are in. How to raise the height confidently, by doing the testing, so the under the conditions. So this is what actually they attempt. So for which, so the we need to do it, so the large, so the large scale testing. Your particle size is actually going to be very high. Okay, now so these are the different mines which are actually there. So this is the material that has been actually collected from the different mine dumps. This is the Talcher and so the other mines. Because we wanted to, for the country, we wanted to finalize some guidelines based on so the testing, etc. We characterized even simple sieving, so the sieve analysis. If you want to do it, so for the large dump sizes, it's a very challenging. Okay, but then what you want? So the what we need is, so we need a direct shear mission. How big it is? It is so big. It is so big, and then this mission, which has been so they established in CMPDA, is the world's largest so the direct shear mission. So the figures of say the dimensions are say the so large. The box size is say 1,000 by 1,000 say the square meters. 1 meter by 1 meter say the square, that is the size of the box. Okay, lower box and upper box, and the whole paraphernalia, if you see it, so the actuators, etc., is mind-boggling. We did it, say 300 by 300, and also so the large so the shear box 1,000 by 1,000. So the whole arrangement looks like that. So for this, so a separate so the gantry and lab is actually created. So part by part, so they are being transported. You see that so you need to have a big effort, so to establish that, so the size of the person and size of the box, if you see it, so and it takes say 3.5 tons of material to fill it up, so for doing the shear test. One single shear test means so that it is a huge. These are the different scenarios of so that, and so based on so the properties, what you get it, so you do the numerical analysis, so the as well, and different bench heights, and then so the you do the testing, and then finally we are so the confidently say that so the your material characteristics are so the improving it, and the conditions in which the dumps are actually presently available. So thereby definitely so there is a possibility of so the raising the dumps with this particular so the facility. So I come to the end of my presentation. What is that we have really seen here? So the strength and deformation behavior of intact rocks, anisotropic rocks, weathered and jointed rock mass under different stress state is modeled through physical modeling, direct testing, and analytical, as well as so several analytical solutions. And say we have proposed it, and then say the numerically also they are being vetted. So as the physical modeling requires a sensitive and robust experimental facilities, we designed and developed. So what is that we did? So the large scale uniaxial, biaxial, polyaxial testing equipment we designed and put to use. Servo controlled static and cyclic direct shear equipment, so they designed. And impact testing facility, this I have not covered, but so the impact and blasting loads is a major issue of late. So thereby, especially the underground structures like tunnels, etc. So we did a separate impact testing facility. Creep mission we have seen, servo-controlled high-pressure triaxial testing facilities, profilometer for the 3D joint mapping, rainfall impact gauges, high-temperature chambers, rainfall impact gauges, so I didn't discuss it because this is for the slope stability, especially we use it, so the rainfall effect and also the seismic effects on the slopes. Rock salt, so the leaching setup also used, so to find the rock salt, so the behavior. These are the few we have created the facilities, so which allowed us to pursue the large range of so the research areas over the years. And then that has actually The sustained approach yielded significant new contributions, methods, criteria to understand the rock and rock mass in totality. See, if you want to do the engineering with the material behavior, so you should actually understand in different loading conditions. And for that, so we need, say these sophisticated, say the equipment. This clarity enabling us to provide the effective solutions to the numerous ground engineering problems and serving the industry. See, if you are solving, say or providing some solutions, say to the industry, it is because of, say these efforts. So I really, say the thank the the LD college and also IGS, so the Ahmedabad student chapter for giving me this opportunity to share some of the developments which are actually taking place at IIT Delhi. And also the teachers, mentors, seniors, colleagues, they all contributed for this. A lot of funding is required for this equipment that is given by the different agencies. And late Jitendra Singh is the main instrument, so the man, because he is the head of the HICO. He was the head of the HICO. So they really provide, so the lot of equipment for our research. And yeah, you see that, say this rock group, these are all my doctoral students. What we call is Geotechnical Research Group, GRG. And these are the doctoral students who have, many of them, so they already got 26 or so, so they have already got received their PhDs. And others are, so they presently they are doing it. And then there is another, so the group which is working, so with so thank you very much, so the thank you very much, so the, for the for the opportunity which you have actually given, so the to present, so the whatever the work which we have been actually doing it. So I'm sorry, so that I might have taken, so the long time.
Not at all, sir. It was really nice to listen you actually. Though you initially told that you are not going to teach, but already you have taken. It was a very comprehensive lecture of this complex material, I will say. And sir, from starting of your various topics which you have covered, from anisotropy of rock to the thermal degradation to influence of PNT and then polyaxial behavior, and then modeling of crystalline rocks, that is micro behavior, and then CNL and CNS, and then viscoelastic behavior, creep behavior, squeezing, then case studies of Rohtang, that is Atal Tunnel, Sabansri, that is power project, and lastly, how you have developed a large scale box shear for CMPDI. So, sir, actually, I really feel that means it was a very nice. Means I don't have any extra words to say. Uh, uh, I, I will request you, sir, that we can have some question answers from the
please, sir.
Participants.
I think so, Ravinder is showing.
Yeah, Ravinder Kumar, have you raised your hand?
Good evening, sir.
Yeah, good evening.
It was a great. It is always a pleasure to listen to Professor Rao, sir. So it is nothing different. And my question is related to stiffness of jointed rock. Probably, I would like to ask to Professor, like, how can we consider the varying normal stiffness in the rock testing system?
How can you
take into account that varying normal stiffness case?
Yeah, normal stiffness, so the I mentioned with jointed rock, isn't it? So because of the asperity, when the asperity is riding over the. No, I think there is a huge echo is coming.
So there is a echo. I can't hear properly.
The amount of normal stress so will be generated because of the rating over the asperity will be inbuilt so in the system. So in the measuring system is such that so that will get affected so in the normal stress. So we are creating so the stiffness surrounding the a particular jointing system. So that stiffness is being so the measured. So I didn't so the elaborately discussed, but there is so the a process by which so when you are shearing it, when the block is actually riding over because of irregular joint or the asperity, and whatever that so the normal stress increment is going to take place because of so the vertical displacement, that is actually the so the will be applied so the in the system.
Okay. So in that we can consider that stiffness with a varying stiffness case we can consider.
Yes, correct. Yeah.
So can I have one more question, please?
Please.
So, sir, it is related to triaxial testing in the field, means especially in the field condition, if we consider. So, if we ignore the effect of sigma to a little bit higher depth, let's say 300 meters or 400 meters or so. So, what will be the effect on stress strain behavior of the rock if we ignore the effect of sigma in the field?
No, see, basically you try to understand, like, if you are ignoring the sigma 2, so what it means, so you are underestimating the strength of the material.
Yes.
See, like, so the uniaxial compressive strength, let us say, like, for a granite, if it is, so the 50 MPa, but, triaxial test, so the even a little bit of confining pressure, you put it and, so the, its strength is going to be 60 MPa or so.
Yes,
So
sir.
now if you sigma 2 is there see in the field, but you are neglecting it. If you neglect it, so you are underestimating the strength. So underestimating means so that you are taking the lower so the range of so the values, which is not really correct, because especially in the tunneling so you have the biaxial stresses are actually acting. You have the vertical stresses are there, you have so the side stresses are there. Only the sigma 3 is so they're going to be 0, because that is along the axis of the tunnel. Isn't it? So you cannot actually neglect in that, because the tunnel may be collapsing it so because of the sigma 2. If you think that sigma 2 is 0 there, so then your side walls are going to get so they're squeezed into the tunnel, and then you may have the problems. So thereby, as far as possible, so for the major structures, in-situ stresses should be properly assessed. So that is one of the reasons underground powerhouses. So we do the hydrofrac test at very deep depths, 500 meters, 1 kilometers below, and you assess the not only the magnitude of the stresses like sigma 1, sigma 2, sigma 3, but also like say the whether horizontally is actually the sigma 3 is so the very positive values 1, 2, 3, etc. See, K0 so the in soils, what is that we take normally so maybe 0.3, 0.4 or so, but in rocks so the especially in the Himalayan rocks, horizontal stresses are much so the severe than the vertical stresses. Yes. So your stress state is so that you need to define for any major project. Okay, accordingly you do the design, like your tunnel shapes. Actually that case I wanted to present it, so the we did say the tunnel in this USBRL project, so the D shape, but that is so the getting subjected to the lot of so the excess stresses and then collapsing it. So thereby we changed the profile so the to the oval shape it so the elliptical shape so that we made it. So thereby but the long axis is so the along the long axis of the ellipse. So the you can rectify the tunnel say subsequently in case if the original design is not actually the correct.
So we can't ignore that effect of sigma 2. It is really very significant.
You cannot. You cannot. You cannot. So you will be first of all underestimating the material, and you may be reading say the conditions which may lead say the failure later. So if you're not reading the conditions properly, you should assess.
Thank you, sir.
Thank you.
Thank you.
Okay, Arpit Parikh, you have one question. Arpit Parikh, you have raised your hand.
Yes.
Yeah.
Yes.
Please,
Yes. Yeah. My question is about rock salt caverns. You discussed about the rock salt caverns, and you have checked some rock salt chunk samples from the Pakistan, right?
Yeah.
So I would like to ask something regarding the basic rock salt caverns capacity, whether it can be used for any oil storage, because oil and again rock salt will interact with on chemical side.
No, I didn't so that gone into those aspects. That the how these so the cavities will be made. It is through the leaching.
Okay.
Okay. Hot water will be sent. So dissolve the salt.
Yeah, I'm asking about the dissolving of the oil into that rock salt caverns.
Yes, that is correct. And then these cavities are always under pressure.
Yeah.
So you like you store the off let's say like so the maybe the oil, and then the rest so you fill it up with so the gas. So you have to, because for the stability of the opening, you need to always maintain the pressure inside.
Okay. Yes. Correct.
Okay.
Yes.
So then only you will be able to pump it also. Like मान लीजिए like so the आपने oil उसमें डाला, and then how do you take it out? So you will be pumping with pressure only. So you will be putting the additional air pressure. Yes, correct. It is through the leaching. We did the leaching experiments.
Okay. If I'm going to do a hydrofracturing or a very deeper depth in the borehole in a weathered rock zone, can we do its simulation in a triaxial test, large scale triaxial test, applying a complete radial pressure through water in our conventional system of triaxial system?
See, you are. I'm not really so the understand what you are, but I can clarify it. See, hydrofrac test is so the to fix the to identify so the stress state. That means sigma 1, sigma 2, sigma 3. Okay, what is the magnitude and what is the direction? Because the stress is also having the directions. So that is the only thing, not any other property.
Okay, that is not
no, they are not connected
to any strength parameters.
No. But so the sigma 1, sigma 2, sigma 3, if you know it, so you will be knowing it, so what could be the strength. You can get it. That is indirectly you can calculate it.
Studies.
Yes.
Okay.
This is the in situ stress. This is the in situ stress.
Yes, in situ stress, correct.
Not the material strength as such.
As such, yes, it is the in situ stresses.
See, if you are going from the surface, if you go 100 meters below, don't you think that there is a water column of rock column of 100 meters acting?
Obviously, once you go to deeper, there must be a water columns.
So that means
there must be a water column always.
Yes, correct. So as you go deep into the earth, so the stress is actually going to increase it.
Increases, yes. I too observe certain kind of behaviors in some weathered rock zones.
I see.
Thank you, sir.
Thank you.
Sir, one small question I want to ask, sir.
Please.
Sir, in our postgraduate geotechnical engineering, we do a small research on rock matrix.
Yeah.
that is where we cut the rock pieces into small blocks, and then we either join by some filling material, or in some case we do not join also them, and then we place that complete cylinder into our triaxial machine. Sir, is there any relevant theory where I would just want to understand that if the upper part of the rock is soft in nature, or let us say of different strength in nature, and the lower part is of different strength in nature, then how the transformation of deformation will take place through the joints?
See, like, what your first part of the question is, say if the rock is having the joints, you do the grouting, isn't it? So that normally we do the grouting, high pressure grouting, so if you do it, cement grout, the cement grout is actually going to go into the openings.
Okay.
The joint is an opening, let us say. So now it is going to bind. The properties are going to improve.
Okay. But sir, actually purpose is to explore that if whatever the joints or the small cracks which have not remained opened, okay, for example during exploration work, but let us say when huge amount of load is coming, okay, or due to the seasonal changes when these cracks are going to get internally opened, then means how this deformation will get transferred to the other part.
It all depends upon orientation of the crack with reference to the loading. See, if it is so the vertical load is actually happening, the joints are horizontal, the joints will get improved, they will close.
Yes, sir.
Okay, so we can, in general,
but that will also depend upon the way I have taken the sample, no sir. But
yes, correct. That is what actually I am telling So what is the direction in which so you are collecting the sample and vis-a-vis your load application.
Okay. Is there any experimental method where I can give partial confinement pressure to the cylindrical sample in rock?
Okay, you want the L/D ratio to sample, full sample, but only the partially you wanted to apply the confining pressure.
Yes, yes. For example, rock length is, let us say L. I want to apply only confining pressure for L/2 only.
No, that is not possible. So in the traction test, because the oil pressure will be there on the surrounding.
Okay, yeah, that I know, sir. But I thought that something might have been developed.
No, but what is the property you want it?
Actually, sir, I just want to simulate that. For example, if there is any rock mass which have been consolidated, let us say partially only, means either due to overburden or due to hydrostatic pressure, means full hydrostatic, not full hydrostatic pressure, then is it possible to simulate same condition in triaxial machine?
No, why not? So that sample separately you do the testing.
But sir, in that case, what will happen, sir? Actually, generally, when we are applying the confining pressure to the full length of sample, okay, what will happen, sir? The rock will fail from the weakest part of the.
No. What I am telling is, so the weaker part, you take the weaker part separately and the stronger part separately and do the testing.
Okay.
No, it is not necessary that you have to do all the time traction test. आपका sample so the छोटा है तो you can do some indirect tests.
Geophysical test.
You can do the point load test.
Okay.
Point load test can be correlated to the consistency.
Yes. Okay. Thank you, sir. Thank you.
Thank you.
Any more questions from attendees?
Good evening, sir.
Good evening.
Yeah.
Sir, this is Dr. Lokesh. First of all, wish you Happy Engineers Day.
Hello.
Yes, sir. Am I on? Sir, myself, Ankesh.
Yeah, Ankesh, how are you?
Fine, sir. How are you, sir?
So very good, yeah. So nice.
And means.
See, participants, so please, Ankesh is, so the assistant prof in SVNIT, and he did his PhD with us, and he did extremely good work. The initial stages, anisotropic rock behavior I presented, so that is part of his work. It's very good. Okay, Ankesh. So,
whenever I see your presentation, it's always something new. So this time, the new topic was there related to Nala. And we were expecting that this thing should come up in coming future. So now we are listening it, and it's very exciting to observe those things. I really wish to visit those places so that I can also have a closer picture on it, look into it. And
next time when I go, I will take you.
I really want to go to such locations, and it's great to hear you every time, sir. And whatever things we have done, those are all because of your support and your thoughts. Whatever your thoughts were.
No, it is all so the combined path. So, but the execution is all done by you people, so the hard work is all you people have done it. So it's that is how actually the groups will form, say it is not that, so your idea, my idea, or your work or my work. It is all combinedly, so that we create, so a good facilities where we can, say solve the major problems. That is more important.
And this platform is also a really good. He was asking questions. He is my student. He's done Antec with me, and now he has joined IIT Wiki. So he is also very excited.
Yeah. I had I forgotten to tell you, so that there are 185 MTech projects were done, so with me. So their contributions are also great, because normally, before PhD a student is finalizing it, it is being tested, so by the MTech students. So part by part, MTech students will vet it, and then thereby, the PhD student, so the will be finally, so the achieving is, so the target. So I take the opportunity that all the MTech students, so their contributions are also a lot of, so the value and immensely, we respect.
In the end, sir, I would like to thank you for such a valuable presentation and all the things which you have mentioned. It's really enhancing our knowledge. Thank you very much, sir.
Thank you.
Thank you, sir. Thank you very much, sir.
Thank you.
Any more questions from attendees? Okay. I think there are no more questions, sir.
Okay.
So, sir, once again, on the behalf of Applied Mechanics Department and LE College, from the bottom of my heart, I really thankful, sir, that you have given us a very deep insight in this subject of rock mechanics, sir. And
so, when you are formulating your course on rock mechanics, or PG or UG, so if any help is required, so we are always there.
Sure, sir. So definitely, sir. Definitely, I will contact you, sir. Definitely, sir.
Okay.
Okay. Thank you, sir. Once again.
Thank you, Rao, sir, for a wonderful presentation. It was a pleasure hearing you.
Thank you.
Thank you, Rao, sir, for.
Thank you. Thank you.
Thank you, sir, for your valuable comments and presentation. It was
Thank you.
nice
Bye bye.
Thank you, sir. Thank you very much, sir.
See you. Thank you. Thank you.
Thank you, sir.
Preeti madam.
Hello.
Preeti madam.
Thank you, Dr. Sir. So,
Preeti madam.
hello.
Yes, madam.
So I will begin my about of the rapid and convey this webinar. Dr. I'm very much thankful to Mr. Parag Dave, owner of MK Soil Testing Laboratory, for sponsoring the entire Dr. R.C. Sonpal Memorial Lecture Series.
Without their generous financial support, it would not have been possible to organize this. I am sure that we will get the same support for our future endeavors too. I would like to extend my sincere thanks to our eminent speaker, Dr. K.S. Rao, for their insightful thoughts of one of the emerging field of geotechnical engineering and accepting our invitation for delivering an expert talk. We have been fortunate to have you with us. My sincere thanks to all the enthusiastic participants without whom this webinar would not have been possible. A very special thanks to Dr. M. V. Shah and Professor S.R. Singh for their dedicated listening and smooth coordination of the program. Now I am concluding this session. As such, it's a RC SONPAL Memorial Lecture Series. We conclude this session beginning another new topic. For another upcoming new session. Thank you all of you.
So thank you all of you. Thank you, madam, very much. And thank you to all the dear participants for attending this session. If you have any suggestions, you can please email me anytime. Okay, my email is available on our LD website also.
Hello, Sangeeta. If you want to say a few words.
Madam, your voice is not coming.
Hello.
Yes, madam.
Sir.
Hello. Hello.
Sanghvi Sahib, sir. Sir.
Yes. Now, sir, we are very much thankful to you for delivering a wonderful lecture. And we are keep on arranging such lectures. It's a series of lectures planned, and we are hopeful that we are going to have some more interesting lectures in the future. And Parag, thank you very much for sponsoring this lecture series, and it is possible only because of your support. Thank you, sir. Yeah. Manish.
Yes, sir.
Yeah, please.
Okay. Thank you, sir. Thank you very much for your kind words. So we will now end this webinar. So thank you once again to all of you, and thank you to the dear participants.